Lab 2, Laboratory Techniques. Materials. You will need a balance, 250 milliliter beakers, 2 of them, a Bunsen burner, copper wire, an evaporating dish, a 100 milliliter graduated cylinder, a heat-resistant mat, sodium chloride, a spatula, test tube, weighing paper, and crucible tong. Introduction. You have applied to work at a company that does research, development, and analysis work. Although the company does not require employees to have extensive chemical experience, all applicants are tested for their ability to follow directions, heed safety precautions, perform simple laboratory procedures, clearly and concisely communicate results, and make logical inferences. The company will consider your performance on the test in deciding whether to hire you and in determining what your initial salary will be. Pay close attention to the procedures and safety precautions because you will continue to use them throughout your work if you were hired in this company. In addition, you will need to pay attention to what is happening around you. Make careful observations and keep a clear and legible record of these observations in your lab notebook. This laboratory orientation session will teach you some of the following techniques: how to use a Bunsen burner, how to handle solids and liquids, how to use a balance, how to practice basic safety techniques in lab work. General safety procedures. The following procedures are necessary for this lab. Wear safety goggles when working around chemicals, acids, bases, flames, or heating devices. Contents under pressure may become projectiles and cause serious injury. If any substance gets in your eyes, notify your instructor immediately and flush your eyes with running water for at least 15 minutes. Secure loose clothing and remove dangling jewelry. Do not wear open-toed shoes or sandals in the lab. Wear an apron or lab coat to protect your clothing when working with chemicals. If a spill gets on your clothing, rinse it off immediately with water for at least 5 minutes while notifying your instructor. Always use caution when working with chemicals. Never taste, touch, or smell chemicals unless specifically directed to do so. Never return unused chemicals to the original container. Follow instructions for proper disposal. Avoid wearing hairspray or hair gel on lab days. Know your schools or homes' fire evacuation routes. Clean and decontaminate all work surfaces and personal protective equipment as directed by your instructor. Dispose of all sharps, broken glass, and other contaminated sharp objects and other contaminated materials, biological and chemical, in special containers as directed by your instructor. Procedure. Copy data tables 1 and 2 in your lab notebook. Be sure you have plenty of room for observations about each test. We already have data tables 1 and 2 in our binder, so we're just going to fill them in as we go. They look like this. Procedure. Record in your lab notebook the location and use of the following emergency items: lab showers, eye wash stations, and emergency telephone numbers. So if you're working from home, like many homeschoolers are, this is a good first stop for your lab shower. After that, it would be a shower. For eye wash, we can use actually bottled eye wash. So we have eye wash, we have a fire blanket, a fire extinguisher, and a first aid kit, all located directly beneath the kitchen sink. As for emergency telephone numbers, most of us have our own cell phones, and you know that if you go to the lock screen and click emergency, it will pull up the emergency call option. Procedure. Number 3. Check to be certain that gas valve on your lab station and your neighboring lab stations are turned off. Notify your teacher immediately if the valve is off because fumes must be cleared before any work continues. So what we use here are small camping fuel containers. So these are the little tanks that you use to take camping. And this one is off, as you can see right here. Procedure number 4. Compare the Bunsen burner in Figure A with your burner. Construction may vary, but the air and methane gas, CH4, always mix in the barrel and the vertical tube in the center of the burner. So because we use camping fuel, ours is not methane, it's actually propane, but it functions pretty much the same way. Procedure number 5. Partially close the air ports at the base of the barrel. Turn the gas on full, hold the sparker, or the torchlight in this case, about 5 centimeters above the top of the barrel and proceed to light. Adjust the gas valve until the flame extends to about 8 centimeters above the barrel. Adjust the air supply until you have a quiet, steady flame with a sharply defined blue light inner cone. If an internal flame develops, turn off the gas valve and let the burner cool down. Otherwise, the metal of the burner can get hot enough to set fire to anything nearby that is flammable. Before you relight the burner, partially close the air ports. Number 6, using crucible tongs, hold a 10 centimeter piece of copper wire 2 to 3 centimeters from the part of the flame labeled A. And then you are going to repeat it for the parts of the flame labeled B, and for the part labeled C. Record your observations in your lab notebook. So you can find a place in your binder for those answers or plug in a separate piece of loose leaf paper and add them there. Number 7, experiment with the flame by completely closing the air ports at the base of the burner. When I close them here, they get bright orange and kind of spray everywhere. Observe and record the color of the flame and the sounds made by the burner. When the burner is set properly, it makes a nice whooshing sound, but it almost makes sort of a fluttering or a kind of a clunky sort of sound when the ports are closed like that and you get the big orange flame. Using crucible tongs, hold an evaporating dish in the tip of the flame for about 3 minutes. Place the dish on a heat-resistant mat, shut off the burner, and after the dish cools, examine its underside and record your observations. After 3 minutes, the bottom of the dish, which started out a nice clean white, looked like this. It is coated in a smudgy layer of sooty mess. Number 8, before using the balance, make sure it is level and showing a mass of 0. If necessary, adjust this calibration knob down here on the end. To avoid discrepancies, use the same balance for all measurements. So you don't want to borrow the balance to the right or left of you. You want to use yours for an entire lab. Never put chemicals directly on the balance pan. So here we've adjusted the calibration knob and we've got it nice and level and on 0, which is not quite where it started. Place a piece of weighing paper on the balance pan and determine the mass of the paper and record its mass to the nearest 0.01 gram in your data table. Ours was 0.4 or 0.40. Put a small quantity of sodium chloride on a separate piece of weighing paper. Then transfer 13 grams of sodium chloride to the weighing paper on the balance pan. Record the exact mass to the nearest estimated 0.01 in your data table. So in this case, if we're going to add 13 grams and our weighing paper was 0.4, then we just are going to add sodium chloride. What we'll do is we're going to move the sliders down so we get 13.4 and add sodium chloride until the balance comes up to level again. Number 10, remove the weighing paper and the sodium chloride from the balance pan. Lay the test tube flat on the table and transfer the sodium chloride into the tube by rolling the weighing paper and sliding it into the test tube. As you lift the test tube to a vertical position, tap the paper gently and the solid will slip into the test tube. So it suggests rolling it, and there is a picture in the lab as well that shows it being rolled, but I wanted to show you this instead. Sometimes rolling it this way like a cigar is a little tricky. So sometimes it's easier to take a slight angle, see there? And then when you roll, it makes a bit of a funnel. And since sodium chloride isn't a dangerous chemical, it's table salt, I can not worry about getting my fingers inside or whatever. If it were a dangerous chemical, we would definitely use gloves. But here you go, and then I'm tapping at the top very gently with one of my fingers on the inside. There we go. And there is our 13.4 grams. Measure the mass of a dry 250 milliliter beaker and record the mass on your data table. Add water up to the 50 milliliter mark to determine the new mass and record the new mass in your data table. Repeat the procedure by filling the beaker to the 100 milliliter mark and then to the 150 milliliter mark and record the mass each time. Subtract the mass of the empty beaker from the other measurements to determine the masses of the water. So there's our 50, and we wrote that information in. And now we're going to go for 100. So if you're doing this lab at home as a cyber student, you're going to want to write these numbers down in your chart and use them as your data. Now we're at 150. Now, so what we did for the next step is we went ahead and went directly with the graduated cylinder. Made a couple steps a little shorter for the sake of this lab. So you're going to repeat steps 11 with the graduated cylinder to measure the volumes of water to the nearest 0.1 milliliter. Read the volumes by using the bottom of the meniscus, which is the curved form by the water's surface. So the lab initially said to measure these out, pour them back into the other beaker, which we very well could have done, but for the sake of time, and basically because our data is going to be very similar, I went ahead and we went directly with the graduated cylinder. So now we're going up to 100 milliliters. And we're going to weigh that, put that on the mass, and make on the balance and see what our mass is. There we go. And we don't have a 150 milliliter option for the 100 milliliter graduated cylinder. So we're just going to go with the first two measurements. Number 13 is to clean up all apparatus at your lab station. Put the wire, sodium chloride, and weighing paper in the containers designated by your teacher. Pour out the water from the beakers into the sink. Scrub the cooled evaporated dish with soap, water, and a scrub brush. Be certain that the gas valves at your lab station and the nearest lab station are turned off. Be sure lab equipment is completely cool before storing it. Always wash your hands thoroughly after lab work is finished and before you leave the lab. Analysis. So let's consider some of our data. Analyzing data here. Based on your observations, which type of flame is hotter? The flame formed when the airports are open, or the flame formed when the airports are closed? What's the hottest part of the flame? And here's your hint. Melting point of copper is 1083 Celsius, 1083 degrees Celsius. That's quite hot. Examining data. Oh, open, of course. Sorry, I forgot to mention that. Open is when our flames are going to be the most streamlined, pretty blue, nice hot flames. And obviously the hottest part is that tippy top, well, not tippy top, but right above the blue cone, right? Which of the following measurements could have been made by your balance? 3.42 grams of glass, 5.66672 grams of aspirin, or 0.000017 grams of paper. Well, the only one of these that our balance could make is this 3.42 grams of glass because it is not as graduated as the other options. We can't get that specific with our mass on the balance. Constructing graphs. Make a graph of the mass versus volume for data in steps 11 and 12. The mass of the water in grams should be graphed along the y-axis as the dependent variable, and the volume of water should be graphed along the x-axis as an independent variable. So this is what we came up with. Here's our mass, and here's our volume. And look and see what you notice. See if you can see any trends. Just look at it for a minute and consider. Interpreting information. When methane is burned, it usually produces carbon dioxide and water. If there's a shortage of oxygen, the flame is not as hot and black carbon solid is formed. Which steps in the lab demonstrate these flames? So when you consider the evaporating dish, when the flame was not as hot, it produced that black carbon solid, which was a byproduct of the methane. Now, if we were using methane, it would have been more obvious than it is with the propane, but still, you get the idea. And that would be step 7. Applying conclusions, which is the most accurate method of measuring volumes of liquids? A beaker or graduated cylinder? Explain why. Well, when you go back and look at the graph that we just had, it becomes really obvious that the graduated cylinder is more accurate. Graduated cylinders are designed for accurate measurements of liquids with a much smaller margin of error than beakers. They are thinner or more narrow than a beaker and have more graduation marks. They are designed to be within 0.5 to 1% of error. Evaluating data. In Madville High School, Gerald got only partway through step 7 of his experiment when he had to put everything away. Soon after Gerald left his lab, drawer caught on fire. How'd this happen? Well, Gerald forgot to shut off his burner. So let's look here at this last bit here. Drawing conclusions. The density of water is equal to its mass divided by its volume. Calculate the density of water by using your data from step 11. Then calculate the density of water by using your data from step 12. So if we do density as mass divided by volume, we look at beakers for 50 milliliters, we had 40.4 grams divided by 50 milliliters, which is 0.8000 grams per milliliter. And if we do it in the graduated cylinder, we have 49.2 divided by 50, and we end up with 0.984 grams per milliliter. And then if we look at the next one down for the 100 milliliter, look at the answer there for beaker. It's 0.885. Well, if you compare the 0.8 and the 0.885 from the beaker to the 0.984 and the 0.985 with the graduated cylinder, it's obvious that the graduated cylinder, at least the answers are much closer together than with the beaker. And interestingly, the actual density of water is 1 gram per milliliter. So which was closer? The graduated cylinder, by a good amount when you're considering tiny numbers. That's it. The end.